What if everything we think we know about the universe is incomplete? Picture the night sky, not as a calm and predictable canvas, but as a living, breathing mystery where the laws of physics themselves seem to bend, break, and rewrite the rules right before our eyes. Stars that shouldn't shine so bright, galaxies spinning too fast to hold themselves together, particles appearing out of nowhere and vanishing without a trace. These aren't scenes from science fiction. They are real cosmic anomalies unfolding across the vast expanse of space, and they are challenging the very foundation of our understanding of reality. Today, we're setting out on a journey to explore 25 of these breathtaking disruptions, phenomena so strange and so profound that they've left even the most brilliant scientists questioning the nature of the cosmos itself. From the eerie influence of dark energy, silently accelerating the expansion of the universe, to the ghostly presence of dark matter holding galaxies together against all odds, each anomaly we'll uncover is a piece of a grand puzzle. These mysteries aren't just academic curiosities. They are urgent, open questions that tug at the edges of known physics, inviting us to look deeper and wonder bigger. This is more than a list of cosmic oddities. It's an invitation to see the universe with new eyes, to recognize that above us lies a frontier rich with enigma and brimming with possibility. By the time we reach the end of our exploration, you won't just have learned about anomalies, you'll have felt their weight, their wonder, and their promise. The night sky will never look the same again, so come with us as we step into the unknown, decode the undecodable, and marvel at a cosmos that is far stranger and far more magnificent than we ever imagined. Imagine staring into the night sky and knowing that every galaxy you see is not just moving away from us, but is actually speeding up on its journey into the void. This isn't a hypothetical scenario, it's our reality. At the end of the last century, two independent teams of astronomers were studying distant stellar explosions known as Type 1, a supernova. These cosmic beacons have a known intrinsic brightness, allowing scientists to precisely calculate their distance. The teams expected to find that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down over time due to the relentless pull of gravity. Instead, they found the exact opposite. The data revealed that the expansion is accelerating, as if some invisible, repulsive force is overpowering gravity itself. This stunning discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011, and it introduced the world to the concept of dark energy. This mysterious energy isn't just a small component of the cosmos. Current measurements suggest it makes up about 68% of the entire universe. Think about that for a moment. The stars, planets, galaxies, and everything we can see and touch account for less than 5% of the cosmic budget. Dark energy is the dominant force shaping the fate of everything. But how do we even know it's there if we can't see it? The evidence comes from multiple, independent lines of investigation. The cosmic microwave background, the faint afterglow of the Big Bang, provides a snapshot of the infant universe. By mapping its tiny fluctuations, satellites like Planck have precisely measured the universe's geometry and composition, and the results consistently point to the existence of this dark energy. Meanwhile, ongoing surveys continue to observe Type 1, a supernova, charting the expansion history and confirming that the acceleration began billions of years ago. The most straightforward explanation for dark energy is something known as the cosmological constant. an idea that Albert Einstein himself introduced and later called his biggest blunder. It represents a constant energy density smoothly filling the vacuum of space. This means that empty space is not nothing. It has a fundamental energy that causes it to push outward. As the universe expands, more space comes into existence, which means more of this repulsive energy, leading to ever faster acceleration. This creates a feedback loop that could ultimately lead to a profoundly lonely and cold fate for the cosmos, known as the Big Rip. In this scenario, the accelerating expansion becomes so powerful that it first tears apart galaxy clusters, then galaxies themselves, then stars, planets, and finally, even atoms and subatomic particles, ripping the very fabric of spacetime apart. Yet, the cosmological constant is not the only idea on the table. Some theorists propose that dark energy is not constant at all, but a dynamic field that has changed over the history of the universe, known as quintessence. Others suggest that Einstein's theory of general relativity, while spectacularly successful, might need to be modified on the largest possible scales. We might be seeing the first signs that our understanding of gravity is incomplete. This is why dark energy is often called the deepest mystery in physics. It forces us to confront the fact that we may be missing a fundamental piece of the cosmic puzzle, a piece that makes up the majority of everything that exists. As we grapple with this enigmatic force pushing the universe apart, it naturally leads us to wonder about its cosmic counterpart, the invisible substance pulling it all together. But if dark energy is the mysterious force pushing the cosmos apart, what is it that holds it all together? This brings us to a second, equally profound cosmic anomaly. Imagine a single galaxy, a vast island of stars spinning in the void. According to the well-established laws of gravity and motion, the stars on the outer edges of that galaxy should be moving much more slowly than those near the dense center. It is a simple principle, much like the planets in our own solar system, where Mercury races around the Sun while distant Neptune plods along its glacial orbit. Yet when astronomers like Vera Rubin began meticulously measuring the rotational speeds of stars in distant galaxies in the 1970s, they found something that defied all expectations. The stars, whether they were close to the galactic core or far out on the dim edges, were all orbiting at nearly the same incredible speed. This was a monumental discovery. The only way this could be possible, the only thing preventing those swiftly moving outer stars from simply flying off into intergalactic space, was if the galaxy contained far more matter than anyone could see. A tremendous amount of invisible mass must be providing the extra gravitational pull to keep everything bound together. This missing mass is what we now call dark matter. It does not emit, absorb, or reflect any light, making it completely invisible to our telescopes across the entire electromagnetic spectrum. We cannot see it, but we can observe its gravitational effects everywhere we look. It acts as the invisible scaffolding of the universe, a cosmic framework upon which the luminous galaxies are built. Current measurements estimate that this mysterious substance makes up about 27% of the universe, meaning there is over 5 times more dark matter in the cosmos than all the ordinary matter that makes up stars, planets, and us. The evidence for dark matter extends far beyond spinning galaxies. One of the most dramatic demonstrations comes from a phenomenon known as gravitational lensing. Einstein's theory of general relativity tells us that mass bends the fabric of space-time, and light travels along this curved path. A massive object, like a cluster of galaxies, can act as a cosmic lens, bending and distorting the light from even more distant objects behind it. When astronomers study these distant, distorted galaxies, they can calculate how much mass must be present in the foreground cluster to cause such extreme warping. Time and again, the mass required is vastly greater than the mass of all the visible stars and gas combined. We are literally seeing the gravitational signature of immense halos of dark matter, bending light itself and revealing its hidden presence. For decades, scientists have been searching for the true identity of this elusive substance. The leading theoretical candidate is a class of particles known as WIMP, or weakly interacting massive particles. These hypothetical particles would be heavy and slow-moving, only interacting with ordinary matter through gravity and the weak nuclear force, making them incredibly difficult to detect. To find them, physicists have built exquisitely sensitive detectors deep underground in abandoned mines and tunnels, shielding them from cosmic rays in the hope that a dark matter particle might, on very rare occasions, bump into an atomic nucleus and create a detectable signal. Other experiments at powerful particle colliders like the Large Hadron Collider are trying to create dark matter particles in high-energy collisions. Another promising candidate is the Action, an extremely light particle that might be detected by the subtle way it interacts with strong magnetic fields. Despite these heroic efforts and decades of searching, dark matter has never been directly detected in a laboratory. It continues to hide in plain sight, its fundamental nature remaining one of the greatest unsolved problems in all of physics. This profound anomaly forces us to accept a humbling truth. The stuff we are made of, the protons, neutrons, and electrons that form every star, every planet, and every living thing, is actually the exception in the universe, not the rule. Most of the matter in the cosmos is something entirely different, something alien and unknown. This invisible matter doesn't just hold individual galaxies together, it also shaped the entire large-scale structure of the universe. In the early cosmos, slight density fluctuations in the dark matter provided the gravitational seeds that ordinary matter could clump around, eventually forming the first galaxies and the vast cosmic web of filaments and voids that we see today. Without dark matter, our universe would look utterly unrecognizable. As we continue to search for answers, we are drawn to places where the known laws of physics break down completely, to the most extreme gravitational environments imaginable. But if dark matter is the invisible cosmic glue holding galaxies together, then black holes are the ultimate cosmic paradox, places where gravity wins so completely that it threatens to unravel the very laws of physics themselves. Imagine taking an entire star, crushing it under its own immense weight into an infinitely dense point called a singularity, and surrounding it with a boundary of no return, the event horizon. Once anything crosses that threshold, it is lost to the universe forever, or so we thought. This simple picture, born from Einstein's theory of general relativity, creates one of the most profound conflicts in all of science, the black hole information paradox. The heart of the problem lies in a fundamental rule of quantum mechanics, the physics of the very small. This rule states that information, the unique identity of every particle, its properties like mass, spin, and charge, can never be truly destroyed. It can be scrambled, transformed, or made incredibly difficult to read, like burning a book to ashes, but in principle, a perfect being could reconstruct the original book from those ashes. The universe, according to quantum law, must keep perfect records, but a black hole born from general relativity seems to be the ultimate criminal, swallowing that information whole and offering no receipt. For decades, physicists assumed the information was simply locked away inside, hidden behind the event horizon. Then, Stephen Hawking made a startling calculation. Hawking discovered that black holes are not entirely black, due to weird and wonderful quantum effects occurring right at the edge of the event horizon. black holes slowly leak a faint glow of particles, now known as Hawking radiation. This radiation causes the black hole to gradually lose mass and, over unimaginable eons, completely evaporate, vanishing from the universe, and here lies the catastrophic paradox. Hawking's early work suggested this radiation was completely random, carrying no information whatsoever about what fell into the black hole. If a black hole evaporates into a featureless cloud of random particles, then all the information about the stars, planets, or books that fell in is irretrievably erased from existence. This violates the core principle of quantum mechanics, creating a fundamental contradiction between our two most successful theories of nature. This set off a decades-long war of ideas among physicists, often called the Black Hole War. On one side were those like Stephen Hawking who, for a time, believed information was truly lost. On the other were physicists like Leonard Susskind, who argued vehemently that information must be preserved, forcing us to revolutionize our understanding of reality. Susskind and others proposed a breathtaking solution, the holographic principle. This idea suggests that all the information describing everything that ever fell into a three-dimensional black hole is not lost inside, but is instead perfectly encoded and preserved on its two-dimensional surface, the event horizon. It's as if the universe acts like a cosmic hard drive, storing a perfect lower-dimensional record of everything that happened, like a hologram. When the black hole evaporates, this information is slowly and chaotically released back into the universe through its Hawking radiation. Other theories are even more radical. The firewall hypothesis suggests that instead of a smooth event horizon, there might be a literal wall of blazing high-energy particles that instantly incinerates anything that crosses it, scrambling its information into the outgoing radiation. While this saves the information, it violates Einstein's principle that someone falling into a black hole should notice nothing special as they cross the horizon, a major point of contention. String theory, meanwhile, offers complex mechanisms where information is transferred via tiny vibrating strings. The debate is far from settled, but the mere existence of this paradox has been incredibly productive, forcing physicists to ask deeper questions about the nature of space, time, and information itself. The implications of this mystery stretch far beyond theoretical physics. If information can be lost, it would undermine the entire foundation of quantum mechanics, which is the basis for technologies we are building today, like quantum computing and quantum encryption. The certainty that information is preserved is what allows us to trust the predictable behavior of the quantum world. Resolving this paradox might not just be about understanding black holes. It could be the key that unlocks a unified theory of quantum gravity, finally marrying the world of the very large with the world of the very small. It challenges us to consider that our everyday concepts of location and information might be entirely illusory, a shadow cast on the wall of a deeper, more complex reality. As we pull our gaze away from these terrifying and enigmatic objects, we find that the universe has woven mystery on an even grander, more impossible scale. Yet as we contemplate the information paradox within the confines of a single black hole, the cosmos reveals a pattern of coordination so vast it defies our most fundamental assumptions about the universe's structure. We now journey to one of the largest and most perplexing scales imaginable, where the brightest objects in the universe seem to be whispering to each other across billions of light years. Quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes actively feeding on surrounding matter. These cosmic beacons are so brilliant they can outshine their entire host galaxies, making them visible across staggering cosmic distances. For decades, astronomers have used them as fixed points to map the geometry of the universe, operating under the long-standing cosmological principle. This foundational idea states that on the largest scales, the universe is both homogeneous, meaning it looks the same everywhere, and isotropic, meaning it looks the same in every direction. There should be no special places and no preferred direction in the grand cosmic scheme. This is why a discovery made by a team of astronomers led by Damien Hutzemakers was so deeply unsettling. By carefully analyzing the light and polarization from nearly 100 quasars, they found that the rotation axes of these incredibly powerful engines, separated by billions of light years, were not randomly oriented as expected. Instead, they showed a surprising degree of alignment, as if they were all subtly coordinated. Imagine spinning tops scattered randomly across a vast floor. Now imagine discovering that a significant number of them, even those on opposite sides of the room, are all spinning on axes that point in roughly the same direction. The sheer scale of this alignment is what makes it so impossible. According to our standard model of cosmology, these quasars are so far apart that they have never been in causal contact with each other. Their regions of space have not had enough time since the Big Bang to exchange any information or influence, not even a signal traveling at the speed of light. They should be completely independent, making any coordinated alignment a statistical miracle. This finding challenges the very bedrock of modern cosmology. If the universe has a preferred direction or a large-scale structure we cannot see, it would force a radical rewrite of our textbooks. So what could possibly be causing such a coordinated display? One compelling hypothesis points to the influence of primordial magnetic fields. These would be magnetic fields generated in the very first moments after the Big Bang, frozen into the fabric of space-time itself as the universe expanded. If such fields exist on a cosmic scale, they could have influenced the way matter collapsed to form the first supermassive black holes, gently nudging their spin axes into alignment over eons. Another exotic possibility involves cosmic strings. These are theoretical, one-dimensional defects in the fabric of spacetime, remnants of the universe's early phase transitions. Think of them as incredibly thin, unimaginably dense cracks in the cosmos, with gravity so intense they could warp the space around them on galactic scales. A network of these cosmic strings could create a preferred direction, a cosmic grain that guided the formation and alignment of structures across the void. The implications are profound. This anomaly doesn't just add a new object to our cosmic zoo, it questions the fundamental symmetry and fairness of the universe itself. Is there a hidden architecture to reality, a framework so large we are only now catching glimpses of it? Confirming or debunking this alignment requires more data from powerful new instruments. The European Space Agency's Gaia mission, which is mapping the positions and motions of billions of stars, is also providing exquisite data on quasars, offering a much larger sample to test this strange correlation. Future observatories like the Square Kilometre Array radio telescope will peer even deeper into the early universe, searching for any hint of a primordial mechanism that could have orchestrated this cosmic ballet. This mystery reminds us that for all our knowledge, the universe may still hold fundamental surprises about its own structure, pushing us from the unimaginably vast down to the incredibly small. From the grand cosmic alignment of quasars spanning billions of light years, we now turn our focus to a mystery on an almost unimaginably small scale, a discrepancy so tiny it could be measured on a kitchen timer, yet it threatens to crack the very foundation of particle physics. This is the puzzle of the neutron lifetime. A neutron, one of the fundamental building blocks of every atom in your body, is not immortal. Outside the stable confines of an atomic nucleus, a lone neutron is radioactive, it will decay, transforming into a proton, an electron, and an anti-neutrino. For decades, physicists have worked to measure the precise duration of its life, and according to every established law of physics, there should be one single definitive answer. But there isn't. The universe is giving us two different answers, and the difference between them is a full minute, an eternity in the world of particle physics. Scientists use two primary methods to measure this lifespan. In the bottle method, ultra-cold neutrons are literally bottled up using magnetic fields or physical containers, and researchers patiently wait and count how many are left after a certain period. This meticulous approach consistently gives a neutron lifetime of approximately 14 minutes and 40 seconds. The other technique, called the beam method, takes a different tack. It creates a beam of neutrons and carefully counts how many protons, the telltale products of their decay, are produced as the beam travels through a known distance. This method, just as precise and rigorous, stubbornly returns a different result, a lifetime of nearly 15 minutes. The two methods, after accounting for every conceivable systematic error and uncertainty, disagree by about 10 seconds. This might not sound like much, but in a field where measurements are routinely made with precision down to fractions of a second, it's a glaring, unresolved chasm that has persisted for over 20 years. Physicists like Benjamin Grinstein have called this a crack in the foundation, and for good reason. The standard model of particle physics, our most successful theory for the subatomic world, demands one lifetime. It predicts with exquisite detail how this decay should proceed through the weak nuclear force. This discrepancy strongly suggests that something is happening in the decay process that we cannot see. The most thrilling possibility is that neutrons are occasionally decaying through a hidden, secret channel into particles that our current detectors are blind to. Imagine a branching path. Most of the time, the neutron takes the well-known road and decays into a proton and electron. But what if once in a while it takes a hidden detour? It could be decaying into dark matter particles, for instance. This would mean that our experiments using the beam method, which count protons, are missing these invisible decay events, making the neutron appear to live longer because fewer protons are produced overall. This single idea connects a laboratory puzzle directly to the greatest mystery in cosmology, the nature of dark matter. The implications of this tiny particle's identity crisis ripple outward to the very beginning of everything. The lifetime of the neutron is not just a number in a textbook. It is a critical parameter that was dialed into the universe during the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis. This was the brief, fiery period where the first atomic nuclei were forged. The rate at which free neutrons decayed directly controlled how much hydrogen fused into helium and trace amounts of other light elements. The precise ratios of these elements that we observe throughout the cosmos today are a powerful test of our entire cosmological model. If the neutron's lifetime was different during this primordial era, it would alter those predicted abundances. The current discrepancy suggests our models of the infant universe might be subtly incomplete, that we might be missing a piece of physics that played a role in building the very first elements. This anomaly even reaches into the most extreme objects in the modern universe, neutron stars. These incredible stellar remnants are essentially giant atomic nuclei, city-sized balls of matter so dense that they are composed almost entirely of neutrons. Their formation, stability, and cooling processes are all governed by the behavior and interactions of neutrons. If free neutrons decay in a way we don't yet understand, it could change our calculations of how neutron stars behave, how they cool down over billions of years, and even how they might interact with potential dark matter. Furthermore, the decay of neutrons is intimately tied to one of physics' greatest questions: Why does our universe consist almost entirely of matter, with virtually no antimatter? The slight asymmetry in the laws of physics that favored matter over antimatter must have operated during these decay processes. A new, hidden decay path for the neutron could provide a fresh clue in solving this profound mystery. It is a staggering thought that the humble neutron, a particle that helps form the very chair you are sitting on, could be the key that unlocks doors to new particles, revises our story of cosmic creation, and explains the ultimate fate of matter itself. This minute-long gap between two experimental results is a siren call to physicists, a sign that there is thrilling, unknown physics waiting to be discovered just beneath the surface of our reality. As we continue to refine these experiments with ever greater precision, we are hunting for the ghost of a decay, a whisper from a hidden branch in the path of a particle's life. And from this microscopic puzzle, we now journey back out to the vastness of our own solar system, where a different kind of anomaly was detected not in a high-tech lab, but in the silent, steady drift of humanity's first interstellar messengers. Yet while the neutron's secret life plays out in ultra-precise laboratory experiments, another anomaly was discovered not in a controlled setting, but on a grand tour of the outer solar system, etched into the faint radio signals of humanity's first ambassadors to the stars. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, were pioneers in every sense of the word. They were the first to travel through the asteroid belt, the first to make close-up observations of Jupiter and Saturn, and the first human-made objects destined to leave our solar system entirely. Long after they completed their primary missions, scientists continued to track them, using the deep space network to listen to their faint whispers across billions of miles. It was during this long, quiet voyage into the void that engineers noticed something peculiar. An incredibly tiny, unmodeled force seemed to be acting on the spacecraft, a constant sunward deceleration of about 10 billion times smaller than the gravity we feel here on Earth. This minuscule pull, just 8.74 times 10 to the minus 10 meters per second squared, became known as the Pioneer Anomaly. For decades, it was a persistent thorn in the side of orbital dynamicists. Every known force was meticulously considered and ruled out. Was it the gravitational pull of unknown objects in the distant Kuiper belt? Calculations showed there wasn't nearly enough mass out there to account for the effect. Could it be the gentle push of the solar wind or the pressure of sunlight itself? Those forces were far too weak, and crucially, they decrease with distance from the sun, whereas the Pioneer Anomaly remained stubbornly constant. Even the drag from tiny particles of interstellar dust was considered and dismissed. The effect was so small that it would have been negligible on a shorter mission, but for these twin probes on their multi-decade journeys, the tiny tug accumulated, creating a navigational drift that grew over time and simply could not be explained. The mystery captivated physicists and sparked a flurry of exotic theories. Some proposed that this was our first hint of modified gravity, a tweak to Einstein's general relativity that would manifest only over very large distances or in very weak gravitational fields, a theory known as modified Newtonian dynamics, or MND. Others wondered if the spacecraft were plowing through a diffuse halo of dark matter trapped by the sun's gravity, its invisible mass providing the extra pull. The possibility that such a precise measurement could reveal entirely new physics was electrifying. The Pioneer Anomaly became a classic example of how careful, long-term data collection can sometimes reveal cracks in our understanding, showing that the most profound discoveries can come from paying attention to the smallest, most persistent discrepancies. The mystery endured for over 30 years, a testament to both the ingenuity of the mission engineers and the patience of the scientific community. The ultimate solution, however, turned out to be not a revolution in physics, but a masterpiece of forensic engineering. A dedicated team led by Slava Turyshev embarked on a digital archaeological dig, recovering decades-old telemetry data and original design documents, even down to the blueprints for the spacecraft's electronics. They painstakingly built a virtual model of the Pioneer probes, and their work revealed a surprisingly mundane culprit: heat. The spacecraft were powered by radioactive plutonium-238 isotopes in their radioisotope thermoelectric generators, or RTG. These units generated a tremendous amount of waste heat, which was dissipated into space through the spacecraft's body. The critical insight was that this heat radiation was not perfectly symmetric. A little more heat was emitted from the back of the spacecraft, which faced away from the sun and had larger cooling fins. According to the simple law of conservation of momentum, every photon of heat radiation carrying energy away from the spacecraft also imparts a tiny amount of thrust in the opposite direction. This anisotropic, or directionally uneven, thermal radiation created a net force that pushed ever so slightly back toward the sun, perfectly mimicking a constant deceleration. When this effect was finely and precisely modeled, it accounted for the vast majority of the anomalous acceleration. It was a brilliant resolution, a victory for careful, meticulous science that managed to explain the seemingly inexplicable. Yet, even with this thermal answer, a whisper of the anomaly remains. A very small residual effect, a fraction of the original signal, still lacks a complete explanation. Some scientists argue it could be due to slight errors in the incredibly complex modeling of the spacecraft's thermal properties, while others still wonder if it might be a sign of something more. The legacy of the Pioneer anomaly is profound. It taught us that to discover new physics, we must first master the old physics to an incredible degree of precision. It demonstrated that a spacecraft is not just a scientific instrument. Its entire structure is part of the experiment, and every watt of power, every bolt, and every sheet of insulation must be accounted for. This relentless pursuit of a signal, from the possibility of new gravity laws to the subtle glow of a warm spacecraft, showcases the scientific process at its best, a relentless drive to understand, to explain, and to leave no stone unturned. This lesson in precision now prepares us to examine particles that arrive at Earth with energies that defy belief, carrying forces that dwarf anything we can create. But if the Pioneer anomaly taught us the importance of meticulous measurement here in our solar system, then the next cosmic disruption shows us that the universe is capable of hurling particles at Earth with energies so immense they defy the very laws we believe govern their journey. We are talking about ultra-high-energy cosmic rays, subatomic bullets traveling at a fraction of the speed of light, each one carrying the kinetic energy of a well-thrown baseball, all compressed into a single, minuscule proton. Detecting one of these particles is an incredibly rare event. You would need a detector the size of a small city to catch just a few per century. But we have detected them, and their existence creates a monumental problem for physics. According to a robust prediction made in the 1960s by Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, such particles simply should not be able to reach us from distant corners of the universe. This prediction is known as the GZK limit. The logic behind this limit is both elegant and inescapable. Imagine one of these ultra-high-energy protons embarking on a multi-million light-year journey across the cosmos. Its path is not through empty space. It is swimming through the faint, cold sea of the cosmic microwave background radiation, the leftover glow from the Big Bang. This background is filled with low-energy photons. For a proton traveling with such unimaginable speed, these harmless photons are transformed. From the proton's perspective, they are blue-shifted into a bath of high-energy gamma rays. When this ultra-fast proton collides with one of these now energetic photons, it can trigger a reaction that produces new particles, most notably a pion. This process saps energy from the proton. Over a long journey, these countless tiny interactions act like a form of interstellar friction, relentlessly bleeding the proton of its energy. The GZK limit calculates that no proton should be able to travel more than about 160 million light-years and still retain an energy above 100 billion electron volts. Beyond that distance, the cosmic microwave background should have sapped it down to a lower energy. The universe, it seems, has built itself a speed bump for particles. And yet, our detectors have recorded multiple cosmic rays with energies far exceeding this limit. This is the heart of the anomaly. How did these particles get here with so much energy still intact? There are two broad, thrilling possibilities. The first is that they come from relatively nearby, within our local cosmic neighborhood of galaxies, and were accelerated by some unimaginably powerful astrophysical engine right next door. The problem is, we don't know of any source within that 160 million light-year range that is capable of such a feat. We look to the usual suspects, active galactic nuclei, where supermassive black holes eject colossal jets of matter, or gamma-ray bursts, the most violent explosions since the Big Bang. But even these extreme events strain our theories of particle acceleration. They would need to operate at nearly 100% efficiency, a level that seems implausible. It would be like finding a cannon in your backyard powerful enough to launch a projectile to the moon. The second possibility is even more radical, that our understanding of physics itself is wrong. Perhaps the GZK process doesn't work exactly as we think. Could there be a violation of Lorentz invariance, a cornerstone of Einstein's special relativity, that would change how these particles interact with the background radiation over such long distances? Or maybe these particles are not protons at all, but heavier atomic nuclei which interact with the background photons differently. However, experiments like the Pierre Auger Observatory in Argentina, a sprawling array of 1,600 water tank detectors spread over 3,000 square kilometers, are working to identify the composition of these rays by studying the giant air showers they create when they strike our atmosphere. The data so far suggests that at the very highest energies, the cosmic rays are indeed likely protons or light nuclei, which only deepens the mystery of their origin and journey. This anomaly is more than just a puzzle about particle travel. It is a direct challenge to our models of the most extreme environments in the universe. These cosmic rays are messengers, and they are telling us about forces and accelerators beyond our current imagination. Solving this mystery requires a global effort. The Pierre Auger Observatory, along with other installations like the telescope array in Utah, constantly scans the skies, not only measuring the energy and composition of these rays, but also trying to triangulate their direction of origin. The hunt is to pinpoint a source on the sky, to find the cosmic cannon that is firing these incredible bullets at us. Every detection is a piece of a puzzle, a clue that could lead us to a new class of astronomical object or force us to rewrite the laws that govern how particles and radiation interact across the vast emptiness of space. These ultra-high-energy particles remind us that the universe is still capable of generating phenomena that push at the very edges of our physical theories, offering a humbling and exciting glimpse into the absolute limits of power and energy in the cosmos. But while these cosmic rays carry whispers of impossibly powerful engines across the void, our next anomaly comes from a far more ancient and universal source, the very afterglow of creation itself. To understand it, we must look back in time to a mere 380,000 years after the Big Bang. the entire universe was a searing, opaque plasma, a thick soup of particles and energy. As it expanded and cooled, the first stable atoms formed, and light, which had been trapped for eons, was suddenly set free. That first flash of light has been traveling ever since, stretched and cooled by the expansion of the universe into a faint microwave glow that uniformly bathes the entire cosmos. This is the cosmic microwave background, or CMB, and it is the oldest fossil we can possibly observe, a baby picture of the universe. Mapping this background radiation has been one of the crowning achievements of modern cosmology. Satellites like NASA WMAP and the ESA's Planck have charted its tiny temperature fluctuations with exquisite precision. These minute variations, mere millionths of a degree, are the seeds of all future structure, the slightly denser regions that would one day collapse to form galaxies and clusters. For the most part, this map confirms our standard model of cosmology beautifully. But there is one glaring, puzzling exception, a spot. Not just any spot, but a vast, perplexingly cold region in the constellation Eridanus that is significantly larger and much colder than our models can easily account for. It's as if you were looking at a perfectly warm, textured blanket spread across the sky and found one large, distinctly chilly patch that shouldn't be there. Scientists have diligently searched for a straightforward explanation. The leading candidate for years was a supervoid. This would be an immense region of space, billions of light years across, that is unusually empty, a cosmic desert with far fewer galaxies and much less matter than the surrounding universe. The theory goes that as light from the CMB passes through such a void, it could lose energy climbing out of the underdense region's gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. This would make the spot appear colder to us. The problem is, when astronomers went looking for this proposed supervoid, they did find evidence of a large underdense region in that general direction, but its size and depth are not nearly sufficient to explain the profound coldness of the spot. The numbers simply don't add up. The void is too small and the spot is too cold. This has forced cosmologists to consider far more exotic and thrilling possibilities. One of the most fascinating theories is that this cold spot is the imprint of a cosmic defect, a relic from the universe's fiery birth. In the incredibly energetic first moments after the Big Bang, the fundamental forces of nature are believed to have undergone phase transitions, much like water freezing into ice. And just as freezing ice can create cracks and imperfections, these cosmic phase transitions could have created defects in the very fabric of spacetime itself. One such hypothetical defect is called a texture. A texture is a knot in the fields that govern the universe, a topological flaw that would have immense gravitational influence. If such a texture existed and collapsed long ago in our cosmic history, it could have created a gravitational well that left a specific, circular signature in the CMB, a signature that looks very much like the cold spot we observe. It would be a direct, observable fossil from a time when the universe was a trillionth of a second old. Perhaps the most mind-bending proposal comes from theoretical physicist Laura Mersini-Houghton, who suggests the cold spot could be evidence of a collision with another universe. In the multiverse theory, our universe is just one bubble in a vast cosmic foam of universes, each with its own distinct physical laws. In this scenario, the cold spot might be the bruise left behind when our budding universe gently bumped into a neighboring bubble universe during its initial inflationary expansion. This collision would have drained energy from our region of space, creating a lasting cold imprint on the CMB. While this idea is highly speculative and controversial, it demonstrates the profound stakes of this mystery. We are not just analyzing a temperature fluctuation. We might be glimpsing evidence of a reality beyond our own, a shadow from a cosmos that operates under entirely different rules. Whether it's a cosmic texture, a multiverse collision, or something else we haven't yet conceived, the CMB cold spot stands as a powerful reminder that our most successful models are still incomplete. It is a tantalizing clue that the primordial universe might have been even stranger and more dynamic than we currently imagine, potentially harboring phenomena that leave echoes across billions of years. This cold patch on the oldest light in the universe challenges us to think bigger and dig deeper, pushing the boundaries of cosmology from the vast scales of the multiverse down to the intricate workings of our own celestial neighborhood. While the CMB cold spot hints at mysteries from the dawn of time, a much closer anomaly has been playing out in the precise and controlled world of orbital mechanics, one that involves the very spacecraft we send to explore our solar system. This is the Flyby Anomaly, a small but persistent puzzle that has emerged when spacecraft swing by Earth to gain a gravitational boost for their long journeys to the outer planets. It's a story of exquisite precision meeting unexplained drift, where the most carefully calculated trajectories sometimes betray a tiny, nagging error. The scenario is a standard one in spaceflight, a maneuver called a gravity assist. To save precious fuel, mission planners use a planet's gravity like a slingshot, allowing a spacecraft to steal a tiny bit of the planet's orbital momentum and accelerate on its way. The physics behind this is rock solid, governed by the immutable laws of Newton and Einstein. Engineers can predict the resulting change in the spacecraft's velocity down to a fraction of a millimeter per second. Yet, during several of these Earth flybys, that prediction has been subtly but undeniably wrong. The first notable case was with the Galileo spacecraft in 1990 as it headed toward Jupiter. As it passed by Earth, tracking stations measured a velocity increase that was 4.6 millimeters per second greater than expected. A tiny number, to be sure, but in the world of interplanetary navigation, where an error of a single millimeter per second can translate to being thousands of kilometers off course at Jupiter, it is a glaring discrepancy. This wasn't a one-time fluke. The same strange boost was seen again with the near-Shoemaker spacecraft in 1998, and then with Rosetta in 2005 and 2007 on its way to a comet. Each time the spacecraft emerged from its Earth flyby, traveling just a few millimeters per second faster than every single computer model said it should. It was as if the planet itself was giving the probes an extra, invisible push on their way out the door. The consistency of the effect is what makes it so compelling to scientists. It points to a real physical phenomenon, not just random noise or a tracking error. Naturally, the scientific community launched a thorough investigation into every conceivable mundane explanation. Could it be atmospheric drag? Even at the high altitudes of these flybys, the Earth's exosphere contains a wispy collection of atoms that could, in theory, impart drag or pressure. But calculations showed this effect was far too small and, crucially, would slow a spacecraft down, not speed it up. What about the pressure of radiation from the sun, or even heat radiation from the spacecraft itself? Again, these forces were meticulously modeled and found to be insufficient to account for the anomaly. The influence of the Earth's tides, the gravitational pull of the Moon and Sun, even the subtle tugs from other planets, everything was factored in, and everything fell short. The anomaly persisted, a ghost in the machine of celestial mechanics. The failure of conventional explanations has opened the door to more speculative and thrilling ideas. Some physicists have wondered if this could be a hint of a slight error in our understanding of gravity itself, perhaps a manifestation of modified gravity laws that only become apparent in specific orbital geometries. Others have looked to the realm of relativity, proposing that the rotation of the Earth, its frame-dragging effect might need to be calculated in a more complex way than currently done. There have even been suggestions that the anomaly could be related to the Earth's magnetic field, interacting with the electrical systems on the spacecraft in some unforeseen way. Yet, none of these proposals have gained widespread acceptance or provided a complete, predictive model that can be universally applied. The Flyby Anomaly, though small, serves as a powerful reminder of the incredible precision of modern science and the humility required to practice it. It shows that even in the well-trodden gravitational field of our own planet, there may still be subtle effects we do not fully understand. For mission planners, it underscores the fact that deep space navigation is not yet a perfectly solved problem. There are still unknowns that must be accounted for with small course corrections. This tiny puzzle pushes our engineering and our physics to be even better, to measure even more precisely, and to remain open to the possibility that the universe still has a few surprises hidden in the details. As we continue to refine our measurements with future missions, the hope is that this anomaly will eventually reveal a new nuance of physics, turning a nagging error into a profound discovery. This pursuit of precision naturally leads us to question something even more fundamental. Are the constants that underpin those very laws of physics truly constant, or could they themselves be changing over the vast expanse of space and time? But if the Flyby Anomaly hints at subtle, unmodeled effects within our own solar system, the next cosmic disruption calls into question the very bedrock of reality itself, suggesting that the fundamental rules of the game might not be fixed but could instead change across the vastness of space and time. We are talking about the fine structure constant, often denoted by the Greek letter alpha. This number is one of the most important in all of physics, a pure, dimensionless constant that governs the strength of the electromagnetic force. It determines how tightly electrons are bound to atomic nuclei, it sets the energy levels within atoms, and it controls the very nature of chemical bonds and the light that atoms absorb and emit. For decades, physics has been built upon a foundational assumption that these fundamental constants are, as their name implies, constant. They are the fixed parameters of the universe, the same everywhere and at every time, providing a stable stage upon which the drama of cosmic evolution plays out. This long-held assumption is now facing a serious challenge from the light of the most distant objects in the universe. Astronomers, led by researchers like John Webb from the University of New South Wales, have been using the world's most powerful telescopes to study the light from quasars billions of light-years away. As this light travels through interstellar and intergalactic clouds on its long journey to Earth, specific atoms in those clouds like iron, magnesium, and nickel absorb very particular wavelengths of light, leaving dark lines in the quasar's spectrum like a unique chemical fingerprint. The precise position of these absorption lines is exquisitely sensitive to the value of the fine structure constant. By meticulously measuring these lines and comparing them to the lines we see produced by the same atoms in laboratories on Earth, Webb's team has gathered evidence suggesting that alpha might have been slightly smaller in the distant past, and crucially, that it might be different in one direction of the sky compared to another. This isn't just a temporal variation, it's a potential spatial one, a dipolar variation across the cosmos. The implications of such a discovery are nothing short of revolutionary. If the fine structure constant is not constant, it would mean that the strength of the electromagnetic force, the force behind chemistry, light, and life itself, was different in other parts of the universe or at different times. This would force a complete rewrite of our textbooks. The entire field of chemistry would be up for grabs, as the periodic table and the rules of bonding would be different in different cosmic eras or locations. Our understanding of the nuclear reactions that power stars would have to be recalibrated. Even the precise dating of astronomical events using known spectral lines could be thrown into question. It would be as if the universal clockwork was running at slightly different speeds in different rooms of the cosmic mansion. This anomaly provides a thrilling potential window into theories that attempt to unify all the forces of nature, such as string theory. Many of these theories naturally predict the existence of extra dimensions of space, dimensions that are curled up and hidden from our everyday perception. In such models, the fundamental constants we observe in our three-dimensional world could actually be projections of more complex physics in higher dimensions. If those extra dimensions are not perfectly static, but can vary in size or shape over time or across space, then the constants they project into our universe would vary along with them. The observed variation in alpha could be the first experimental hint that these extra dimensions are real, a faint echo from the full, higher dimensional nature of reality. Naturally, a claim this extraordinary faces intense scrutiny and demands extraordinary evidence. The measurements are at the very limit of our technological capabilities, and potential systematic errors are a major concern. Could unknown instrumental effects in the telescopes be mimicking this signal? Could the absorption lines be contaminated or shifted by other unknown physical processes in the interstellar clouds? The debate is ongoing, with other teams using different methods and instruments, sometimes confirming and sometimes contradicting the findings. This healthy scientific tension is driving the development of even more precise observational techniques, using next-generation telescopes like the Extremely Large Telescope to put this tantalizing anomaly to the ultimate test. The mere possibility that our physical constants might be inconstant forces us to confront a profound philosophical question. Are the laws of physics truly universal laws, or are they merely local bylaws, subject to change as we travel through the cosmos? This questioning of fundamental forces on a universal scale finds a curious parallel when we look closer to home, at the seemingly simpler motion of stars within their galaxies. This brings us to a galactic mystery that strikes at the very heart of the dark matter debate, one that emerges not from what we can't see, but from a startlingly precise pattern in what we can. For decades, the primary evidence for dark matter has been the observation that stars orbit their galaxies far too quickly, their motion implying the presence of vast, invisible halos of mass. But what if we've been asking the wrong question? Instead of focusing on the mismatch, a team of astronomers led by Stacy McGaw and others began looking for a pattern in the data itself. They took measurements from over 100 galaxies of all types: spirals, dwarfs, irregulars, and plotted a simple graph. On one axis, they put the observed gravitational acceleration felt by stars and gas within those galaxies, measured by their orbital speeds. On the other axis, they placed the gravitational acceleration that should be produced by the visible matter alone, all the stars, gas, and dust we can actually see. The result was nothing short of astonishing. The data points didn't scatter randomly across the graph. Instead, they fell into an incredibly tight, smooth curve. This is the radial acceleration relation, or RAR. It reveals a precise, predictable rule. If you know the gravitational pull from the visible matter in a galaxy at any given point, you can predict the total observed acceleration with near-perfect accuracy. This relationship holds true across a breathtaking range of galaxy sizes and masses, from tiny, faint dwarf galaxies to the largest spirals. It's as if every galaxy in the universe is following a single, simple instruction manual for gravity, one that connects the seen and the unseen in a fundamental way. The existence of this clear pattern is a monumental challenge for the standard dark matter model. In that model, the dark matter halo and the visible galaxy are two separate components that evolve together but through different, complex processes. The dark matter halo forms first through gravitational collapse, and then the ordinary gas cools and falls into it to form stars. Because of this separate history, there's no obvious reason why the gravity from the visible matter should be so exquisitely predictive of the gravity from the dark matter at every single location within a galaxy. To reproduce this tight correlation, the dark matter model requires a very specific and seemingly fine-tuned interplay between the distribution of ordinary matter and the distribution of dark matter. It can be done, but it feels like fitting a very complex and contrived solution to a beautifully simple problem. This elegant simplicity is precisely why some physicists see the radial acceleration relation as powerful evidence for a radically different idea, that we've been misunderstanding gravity itself all along. The leading alternative is a theory called modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the 1980s, MND suggests that Newton's laws of gravity, and by extension Einstein's, need a slight modification at very low accelerations, the kind found in the outskirts of galaxies where gravity is incredibly weak. Milgrom's simple formula predicts that below a certain acceleration threshold, the force of gravity stops fading with the square of the distance and instead follows a different rule. Remarkably, this simple modification naturally predicts a relationship between visible mass and observed acceleration that looks exactly like the radial acceleration relation. For its proponents, the RAR isn't a puzzle to be solved. It's the predicted outcome of a new law of nature. The debate between these two interpretations is one of the most passionate in modern cosmology. Is the universe filled with a mysterious, invisible substance that just happens to be distributed in a way that perfectly mimics a simple, modified gravity law? Or is the universe trying to tell us that our understanding of gravity, which has been so successful in our solar system, breaks down on the vast scales of galaxies? The RAR doesn't definitively prove one side over the other, but it elevates the discussion. It forces the dark matter community to explain not just the existence of missing mass, but the origin of this stunningly precise pattern. It gives the modified gravity community a clear, empirical prediction that their theory got right decades before the data was good enough to confirm it. This isn't just an academic debate. It's a fundamental inquiry into whether the cosmos is dominated by an unseen particle, or whether we need to rewrite the rules of motion that have guided us since Newton. This intimate connection between what is seen and what is felt on a galactic scale finds a strange parallel when we zoom out to the largest scale imaginable, where a different kind of tension is pulling our cosmological model in two opposing directions. Yet as we grapple with the elegant but puzzling radial acceleration relation within individual galaxies, a far grander and more consequential tension is emerging across the entire observable universe, one that threatens to split our standard model of cosmology right down the middle. This is the Hubble tension, and it centers on a single, crucial number, the Hubble constant, denoted as h0. This number is nothing less than the current expansion rate of the universe. It tells us how fast, at this very moment, galaxies are receding from us for every megaparsec of distance, about 3 million light-years. Pinpointing this number is one of the most important goals in all of cosmology, because it sets the age of the universe, determines its ultimate fate, and acts as a fundamental benchmark for every cosmological theory. For decades, astronomers have been working to measure this number with ever-increasing precision, and they have become incredibly good at it. The problem is, they are now getting two very precise but stubbornly different answers depending on how they look. One path to measuring the Hubble constant is to look back into the deep past to the very earliest light we can see, the cosmic microwave background. The Planck satellite, which mapped the CMB in exquisite detail, provides a snapshot of the infant universe at just 380,000 years old. By meticulously analyzing the tiny fluctuations in this background radiation and feeding them into our incredibly successful standard model of cosmology, known as lambda cold dark matter, scientists can predict how the universe should have evolved and what its expansion rate should be today. This method, which relies on physics from the dawn of time, gives us a Hubble constant value of about 67.4 kilometers per second per megaparsec. This is the universe's expansion rate as forecast from its baby picture. The other path is to measure the expansion rate directly in our contemporary universe. This is called the distance ladder method, and it's a painstaking process of cosmic cartography. Astronomers like Nobel laureate Adam Rees and Wendy Friedman use incredibly reliable celestial landmarks, such as Cepheid variable stars and Type Ia supernova. These objects have a known intrinsic brightness, so by measuring how bright they appear to us, we can calculate their distance. By then measuring how much the light from their host galaxies is redshifted stretched by the expansion of the universe, we can directly calculate how fast the universe is expanding right now. This local, direct measurement consistently returns a higher value, about 73.0 kilometers per second per megaparsec. The difference is about 10%, a gap that has persisted and even grown as measurements have become more and more precise, with error bars now so small that the two values are separated by a chasm of over 5 standard deviations. This is no longer a minor discrepancy, it is a significant and persistent tension. This isn't just a case of one measurement being slightly off. These are entirely independent methods, each backed by decades of work and multiple cross-checks. The early universe measurement from Planck is a model-dependent inference, but it is a model that has been spectacularly successful at predicting a vast array of other cosmological observations. The late universe measurement is a direct, empirical observation of the cosmos around us. Both sides are conducted by world-class experts, and both sides are confident in their results. The unnerving conclusion is that both cannot be correct. This Hubble tension suggests that our otherwise triumphant standard model of cosmology might be missing a crucial ingredient. The most exciting possibility is that this ingredient is new physics, a phenomenon not currently accounted for in our equations. One compelling idea is known as early dark energy. This theory proposes that in the very first few 100,000 years after the Big Bang, there was an additional, transient form of dark energy that briefly surged and then faded away. This extra energy would have subtly changed how the early universe evolved, which would in turn alter the predictions from the cosmic microwave background for what the Hubble constant should be today. If this early dark energy existed, it would effectively nudge the Planck prediction upward, potentially bringing it into beautiful agreement with the higher local measurements. Other theories suggest that dark matter might have properties we don't understand, perhaps interacting with itself or with radiation in ways that would affect the expansion history. There's even the possibility, however remote, that the discrepancy points to something as profound as a flaw in Einstein's theory of gravity itself, a crack in the foundation of general relativity that only becomes apparent on the largest cosmic scales. The resolution of this tension is one of the most urgent quests in modern cosmology. Astronomers are deploying every tool at their disposal to break the deadlock. Wendy Friedman's team is pioneering new methods using the tip of the red giant branch, a different type of star that provides an independent check on the distance ladder, free from the potential calibrations that affect Cepheid variables. New observatories like the James Webb Space Telescope are now peering into the universe with unprecedented clarity, measuring the properties of Cepheid variables and supernova in distant galaxies with less interference from cosmic dust, hoping to reduce the uncertainties in the local measurement to an absolute minimum. At the same time, next-generation SIMBI experiments are being planned to map the faint afterglow of the Big Bang with even greater precision, searching for any subtle signature of that proposed early dark energy or other exotic phenomena. The hope is that these powerful new eyes on the cosmos will finally reveal whether the problem is a tricky systematic error we haven't yet caught, or if we are truly on the verge of a revolution that will introduce a new chapter in our understanding of cosmic evolution, forcing us to embrace a new and even more wondrous cosmological paradigm. While the Hubble tension reveals a potential crack in our understanding of the universe's expansion, a different kind of transformation is occurring on a subatomic scale, one that involves the most elusive and ghostly particles known to science. For a long time, neutrinos were thought to be the simplest of particles, tiny neutral wisps of matter that zipped through the cosmos at the speed of light, barely interacting with anything. The original standard model of particle physics, that magnificent theory that describes the fundamental building blocks of everything, declared them to be completely massless. But the universe, as it so often does, had a surprise in store. It turns out that neutrinos have a secret identity crisis. They are not one, but three distinct types: the electron neutrino, the muon neutrino, and the tau neutrino. And as they travel, they do not remain faithful to a single identity. They spontaneously and continuously oscillate, morphing from one type into another as they journey through space. This incredible phenomenon, known as neutrino oscillation, is like watching a chameleon change colors as it moves across different leaves. Imagine you have a beam of pure muon neutrinos coming from a particle accelerator or from the heart of the sun. If you set up a detector a certain distance away, you would not find only muon neutrinos. Some of them will have transformed into tau neutrinos. Wait a little longer, travel a little farther, and some may have changed back. This metamorphosis is only possible if neutrinos have mass, a property the original standard model explicitly forbade. The different neutrino types must have slightly different masses for this quantum mechanical ballet to occur. The discovery of this behavior was so revolutionary, so fundamentally disruptive to our established laws, that it earned the researchers behind two key experiments the Nobel Prize in Physics in 2015. The first crucial discovery came from the Super Kamiok and detector in Japan, a colossal underground tank filled with 50,000 tons of ultra-pure water, surrounded by incredibly sensitive light sensors. This experiment was designed to catch neutrinos produced when cosmic rays strike the Earth's atmosphere. They found a telling discrepancy. Muon neutrinos arriving from directly above the detector were plentiful, but those that had traveled through the entire Earth to arrive from below were mysteriously scarce. The only logical explanation was that during the longer journey through the planet, a significant fraction of those muon neutrinos had oscillated into tau neutrinos, which the detector at that time could not see. This was the first strong evidence that neutrinos were changing their identities. The case was sealed by the Sudbury Neutrino Observatory in Canada, which used 1,000 tons of heavy water to study neutrinos coming from the sun. Solar models had long predicted a certain flux of electron neutrinos, but experiments had consistently detected only about a third of that number, a puzzle known as the solar neutrino problem. SNO's genius was its ability to detect all three types of neutrinos. Their results showed conclusively that the total number of neutrinos arriving from the sun matched predictions perfectly. The missing electron neutrinos hadn't vanished, they had simply changed into muon or tau neutrinos on their journey to Earth. The mystery was solved and a new one was born. Neutrinos have mass. This discovery, while answering one question, opened a Pandora's box of others. The fact that neutrinos have mass, however tiny, means the standard model is incomplete and must be revised. It immediately connects to one of the greatest mysteries in all of cosmology. Why does our universe consist almost entirely of matter, with virtually no antimatter? The laws of physics, as we currently understand them, should have produced equal amounts of both during the Big Bang, which would have led to their mutual annihilation, leaving behind a universe of pure energy. The fact that we exist is proof that a fundamental asymmetry called CP violation must have favored matter. The oscillations of neutrinos and their antimatter counterparts, antineutrinos, could be a key player in this process. If neutrinos and antineutrinos oscillate at slightly different rates, they could have tipped the scales in the early universe, allowing a small surplus of matter to survive and eventually form everything we see today. Furthermore, the minuscule masses of neutrinos suggest the potential for entirely new physics beyond the standard model. Many theorists now believe that the neutrinos we observe could be mixing with a hypothetical fourth type, a sterile neutrino. This particle would be even more elusive, interacting only through gravity and not the weak force, making it a prime candidate for dark matter. The implications of these ghostly particles also extend to the most violent events in the cosmos. When a massive star collapses in a supernova explosion, 99% of its energy is released not in light, but in a tremendous burst of neutrinos. These particles dictate the very mechanics of the explosion, and their oscillations en route to Earth can change the flavor of neutrinos we detect, which in turn affects how we interpret the inner workings of these stellar cataclysms. They are the universe's silent messengers, and their ability to change form makes them both a challenge to decipher and a powerful tool for probing the most extreme environments, from the sun's core to the remnants of dying stars, forcing us to rewrite the textbooks on both the smallest and largest scales of existence. While neutrinos reveal their subtle transformations on a subatomic journey, another invisible force weaves through the cosmos on a truly monumental scale, one that you can actually hold in your hand with a simple compass. Magnetic fields are not just a terrestrial phenomenon, they are a fundamental, though enigmatic, feature of the entire universe. They stretch between galaxies, thread through colossal galaxy clusters, and are woven into the very fabric of interstellar space. We've detected their presence by observing how they polarize the light from distant quasars and influence the paths of high-energy cosmic rays. Their strength, while vastly weaker than a common refrigerator magnet, is remarkably consistent across billions of light years. This cosmic ubiquity presents a profound puzzle. Where did these immense magnetic fields come from, and how have they maintained their coherence across such unimaginable voids? The leading theories for their origin split into two captivating camps. The first suggests a truly primordial beginning. In this scenario, magnetic fields were born in the unimaginable chaos of the very early universe, potentially during a period of rapid expansion known as inflation. Quantum fluctuations during this epoch could have generated tiny seed fields, which were then stretched across cosmic scales to become the weak but widespread foundations we detect today. Another primordial idea involves phase transitions in the infant cosmos, moments when the fundamental forces of nature split from one another. Just as swirling patterns can form in water as it freezes into ice, these cosmic shifts could have generated currents and, in turn, magnetic fields that were imprinted onto the fabric of spacetime itself. These theories are elegant because they provide a universal starting point, a genesis event for magnetism that affects the entire cosmos simultaneously. The second major theory points to a more localized but no less dramatic origin story, the astrophysical dynamo, This process takes a tiny, pre-existing seed field, which could itself be primordial, and amplifies it through the churning motion of ionized gas. Imagine a simple electric generator, but on a galactic scale. As a galaxy rotates, its plasma swirls and twists, stretching and winding magnetic field lines. This motion can take a weak magnetic field and turn it into the powerful, organized structures we observe today, much like a spinning turbine generates electricity. This dynamo effect is thought to be responsible for the magnificent spiral magnetic fields observed in galaxies like our own Milky Way. However, the dynamo theory has a chicken and egg problem. It needs a small seed field to get started. Where did that initial, faint magnetic field come from? This is where the two theories often collide and combine, with primordial fields providing the seeds for astrophysical dynamos to amplify. Regardless of their origin, the influence of these cosmic magnetic fields is anything but subtle. They play a crucial role in the birth of stars. Within giant molecular clouds, magnetic fields provide support against gravitational collapse. They act like a cosmic scaffolding, controlling the rate at which gas can condense to form new stellar nurseries. Without this magnetic pressure, galaxies might have burned through their gas too quickly in a frenzy of star formation. These fields are also the universe's ultimate particle accelerators and guides. Charged particles, like the protons that make up cosmic rays, cannot travel in straight lines through a magnetized universe. They spiral along magnetic field lines, which forces them to travel much greater distances before reaching our detectors. This makes pinpointing the origin of these high-energy particles incredibly difficult, as their paths are scrambled by the magnetic maze they must navigate. Furthermore, magnetic fields can confine and shape the incredibly hot gas that fills the spaces between galaxies in massive clusters, influencing the growth of the largest structures in the universe. The enduring mystery of cosmic magnetism pushes our observational capabilities to their limits. Scientists are using sophisticated radio telescopes to map the polarization of light across the sky, searching for the faint imprint of these fields. Each new observation helps to constrain the theories, telling us whether the fields are truly primordial or primarily astrophysical in nature. Unraveling this mystery is key to a complete understanding of cosmic evolution, from the first moments after the Big Bang to the formation of the stars and planets we see today. These invisible threads of force, silently guiding and shaping the cosmos, remind us that the universe is governed by more than just gravity. It is a place where electromagnetism, born in either the fires of creation or the engines of galaxies, holds a profound and silent sway over everything. Yet as we chart the vast magnetic fields that shape galaxies and guide cosmic rays, we encounter a cosmic accounting error on a much smaller scale, one that involves a humble element forged in the universe's first fiery minutes. The story of the universe's birth is written in the abundances of the lightest elements: hydrogen, helium, and tiny traces of lithium. According to our incredibly successful theory of Big Bang nucleosynthesis, the entire cosmic recipe was cooked up in just the first 20 minutes after the Big Bang, when the entire universe was a searing hot nuclear fusion reactor. The predictions for hydrogen and helium match the observed values in the oldest stars and primordial gas clouds with stunning, almost miraculous precision. But for lithium, something is deeply wrong. The math says there should be about 3 times more lithium-7 in the oldest stars than we actually see. It's as if the universe's ledger is missing a crucial entry, a discrepancy that has cosmologists and nuclear physicists scratching their heads. This is not a small oversight. The predictions of Big Bang nucleosynthesis are a cornerstone of modern cosmology. They are one of the 3 great pillars of evidence for the Big Bang model, alongside the expansion of the universe and the cosmic microwave background. The fact that they work so well for deuterium and helium makes the lithium problem stand out like a sore thumb. It suggests that our understanding of those first few minutes, a period we thought we had down to a science, might be incomplete. The anomaly is particularly puzzling because it doesn't involve complex later processes. It's a direct challenge to our models of the primordial universe itself, a time when conditions were supposedly simple and pure. Scientists have pursued several intriguing paths to solve this mystery. One possibility is that our understanding of nuclear physics itself is incomplete. The rates of specific nuclear reactions that created and destroyed lithium in that primordial soup are calculated from laboratory experiments. Perhaps there is an unknown or mismeasured reaction pathway that destroyed more lithium than our models account for. Another compelling idea points the finger at the stars themselves. The oldest stars in our galaxy, known as population 2 stars, are the time capsules we use to measure primordial lithium. It's possible that over their billions of years of life, these stars have somehow destroyed or processed the lithium in their outer layers, perhaps by dragging it down into their hot interiors where it could be fused into heavier elements. However, stellar models struggle to explain the uniform depletion we see across so many different types of ancient stars. The most thrilling possibility is that the lithium problem is a hint of new physics operating during the Big Bang. Could unknown particles have been present, altering the reaction rates? Some theories suggest that if dark matter particles interacted with the primordial plasma in a specific way, they could have affected the balance of protons and neutrons, which would have cascaded down to change the final lithium yield. Others have considered whether the fundamental constants of nature, like the strength of the nuclear force, might have been slightly different in that extreme environment. Each of these ideas is a potential gateway to a deeper theory, a sign that the infant universe may have been even stranger and more complex than we currently imagine. The implications of this tiny mismatch are profound. Lithium is the third element in the periodic table, and its abundance is a sensitive probe of the density of ordinary matter in the early universe. If we cannot accurately account for it, our estimate of the total amount of normal matter in the cosmos, a critical parameter in our cosmological models, could be slightly off. Furthermore, this puzzle connects the largest scales of cosmology to the smallest scales of particle physics, showing how a discrepancy in the amount of a single element can force us to question our most fundamental theories about the nature of reality. It is a powerful reminder that in science, the smallest details can often point to the biggest revolutions, urging us to look closer at the vacuum of space itself, where another subtle effect defies our everyday expectations. Yet as we ponder the missing lithium from the universe's earliest moments, we encounter a phenomenon that proves nothing is ever truly missing, not even in the deepest vacuum of space. Imagine two perfectly smooth, uncharged metal plates placed excruciatingly close together in a complete vacuum, a place we normally think of as utterly empty. According to the classical physics of the 19th century, absolutely nothing should happen. There is no gravity, no electric charge, no obvious force to act between them. But when Dutch physicist Hendrik Casimir performed the calculations in 1948, he predicted something astonishing. The plates would be pulled together by an invisible, irresistible force. 2 decades later, experimentalists confirmed it. This is the Casimir effect, and it is one of the most direct and mind-bending demonstrations that what we call empty space is anything but empty. The secret lies in the bizarre rules of quantum mechanics. At the tiniest scales, the vacuum of space is not a still, silent void. It is a seething, bubbling froth of quantum activity. The Heisenberg uncertainty principle tells us that energy cannot be precisely defined for very short periods of time. This allows for virtual particles to spontaneously pop into existence everywhere, borrowing energy from the vacuum before annihilating each other and returning it almost instantly. Think of it as a cosmic foam where pairs of particles and antiparticles are constantly flickering in and out of reality. This endless dance of creation and destruction means that even the complete vacuum of space possesses a fundamental energy, a background hum of existence known as zero-point energy. Now place those two metal plates incredibly close together. Their presence imposes a new rule on this quantum foam. Only certain wavelengths of light, certain frequencies of vibration, can fit between the plates. The space between them is like a tiny musical instrument that can only play specific notes. Outside the plates, however, the quantum vacuum can hum with vibrations of all possible wavelengths. This creates a pressure imbalance. There are simply more virtual particles and quantum fluctuations pushing on the outside of the plates than there are pushing on the inside. The result is a net force that pushes the plates together. It's not a force from anything we can see or touch. It is a force generated by the absence of possibility, by the restriction of what can and cannot exist in the space between them. This has been measured with exquisite precision, and it matches Casimir's predictions beautifully. The confirmation of this effect was a triumph of quantum theory, but it also opened a Pandora's box of cosmological questions. If every cubic centimeter of empty space is brimming with this zero-point energy, then the collective energy of the entire universe's vacuum should be colossal. When theorists try to calculate this total vacuum energy and its gravitational effect, they arrive at a number that is absurdly, impossibly large, about 120 orders of magnitude stronger than the observed effect of dark energy that is accelerating the universe's expansion. This is often called the worst prediction in all of physics. It represents a staggering discrepancy between theory and observation, suggesting we are missing a crucial piece of understanding about how quantum physics and gravity interact on the largest scales. Some physicists believe there must be a cancellation mechanism we don't yet understand, or that the nature of vacuum energy is far more subtle than our current math can capture. Beyond its profound philosophical implications, the Casimir effect has very real, practical applications in the emerging world of nanotechnology. As engineers build machines on the scale of micrometers and nanometers, these quantum forces become significant. They can cause the moving parts of tiny devices to stick together, a phenomenon known as stiction that is a major design hurdle, but this force can also be harnessed. Scientists are exploring ways to use the Casimir effect to create frictionless bearings for nanoscale machines, or to develop new types of switches and sensors that are actuated by nothing more than the restless energy of the quantum vacuum itself. It's a stunning example of how a deep, fundamental discovery about the nature of reality can eventually find its way into the technology of tomorrow. This undeniable proof that nothing is truly empty forces us to reconsider the very fabric of the cosmos, a lesson we must now apply to the largest structures we know. But if the Casimir effect shows us the restless energy hidden within the void, our next cosmic puzzle takes us back to the grand architecture of dark matter, where the most powerful supercomputers in the world are painting a picture of the cosmos that doesn't quite match what we see outside our window. This is the too big to fail problem, and it begins with a virtual universe inside a machine. Cosmologists have spent decades building incredibly sophisticated simulations of how our universe evolved. These aren't simple animations, they are mathematical universes governed by the precise equations of gravity and the standard model of cosmology, known as lambda cold dark matter. We feed in the initial conditions from the cosmic microwave background, press play, and watch as billions of years of cosmic history unfold over months of supercomputer time. These simulations are a triumph of modern science, successfully predicting the vast cosmic web of filaments and voids and the general distribution of galaxies we observe. But when we zoom in on the finer details, specifically on the smallest galaxies that orbit larger ones like our Milky Way, the simulation and reality start to dramatically disagree. The issue revolves around dark matter halos. In these virtual universes, the dark matter doesn't just form a smooth cloud around a galaxy. It clumps into thousands of smaller subhalos like lumps in a cosmic gravy. According to the physics programmed into the simulation, the most massive of these subhalos are so enormous and have such strong gravity that they should easily attract enough gas to form bright, bustling satellite galaxies packed with stars. They are, in the parlance of the field, too big to fail at galaxy formation. The computer confidently predicts that a galaxy like the Milky Way should be surrounded by a swarm of dozens of these large, bright satellite galaxies. But when we look up at our own sky and at the environs of other nearby galaxies, we find a very different story. We do see satellite galaxies, like the Large and Small Magellanic Clouds, but we find far fewer of these big, bright ones than the simulations insist should be there. It's as if the universe has a missing satellite problem, but specifically for the largest and most massive ones. The virtual universe is overproducing giants, while the real universe seems to prefer smaller, fainter companions. This discrepancy forces a fascinating confrontation between theory and observation. If our understanding of dark matter is correct, then why don't the observations match the simulations? Scientists have proposed two broad categories of solutions, each with profound implications. The first idea takes aim at the very nature of dark matter itself. The standard model assumes cold dark matter, meaning the particles are slow-moving and heavy. But what if dark matter is slightly warmer? Introducing warm dark matter, consisting of lighter, faster-moving particles, could resolve the issue. These faster particles would have more energy, preventing them from collapsing into as many small, dense clumps in the early universe. This would suppress the formation of the very smallest halos, effectively erasing the tiniest satellites and potentially explaining why we don't see as many large ones. Perhaps the largest satellites we do see are the survivors of this suppression. This would be a fundamental shift in our search for dark matter, redirecting efforts from heavy WIMP to lighter particles like sterile neutrinos. The second major solution keeps dark matter cold, but changes the story of how galaxies form within these halos. Perhaps the dark matter halos are indeed there, massive and numerous, but they are just empty ghost halos devoid of stars. Why wouldn't they form galaxies? The answer could lie in the complex and violent physics of star formation itself. When the first stars ignite in a small galaxy, they don't just shine, they unleash tremendous winds and erupt in supernova explosions. This feedback can blow huge amounts of gas right out of the shallow gravitational well of a small dark matter halo, starving it of the fuel needed to make future generations of stars. It's like trying to light a campfire in a hurricane. The ingredients are there, but the environment is too hostile for anything to catch hold. In this scenario, only the halos that formed their stars very early, before this feedback became too intense, or those that reside in particularly quiet neighborhoods, manage to become the bright satellites we see today. The rest remain dark, invisible monuments to the fierce temper of infant stars. The too big to fail problem is more than just a technical mismatch. It is a crucial stress test for our entire cosmological paradigm. It forces astrophysicists to refine their simulations, adding ever more detailed physics of gas, stars, and supernova to see if they can make the virtual universe look more like our own. It challenges particle physicists to consider a wider range of possibilities for what dark matter could be. This anomaly exemplifies the scientific process at its best, a constant dialogue between prediction and observation, where even the most successful models are pushed to their limits in the pursuit of a deeper, more complete truth. The resolution will likely teach us not just about the invisible dark matter skeleton of the cosmos, but also about the fiery, feedback-driven processes that bring light to the universe. This intricate dance between the dark and the luminous prepares us to question an even more fundamental constant, one that has defined the absolute limit of speed in our universe for over a century. But if the too big to fail problem challenges our understanding of dark matter on a galactic scale, our next anomaly strikes at the very heart of Einstein's theory of relativity itself, questioning one of the most sacred constants in all of physics. For over a century, the speed of light in a vacuum has been enshrined in physics as c, an immutable constant that is exactly 299,792,458 meters per second. This isn't just a number, it's a fundamental pillar of our understanding of the universe, the ultimate speed limit for causality, the conversion factor between space and time in Einstein's famous equation, and the foundation upon which all of modern physics is built. The constancy of c is so deeply assumed that it is built into the very definition of the meter itself. Yet a small but persistent group of physicists have dared to ask a heretical question: what if this constant wasn't always constant? What if the speed of light was different in the fiery moments of the early universe? This radical idea, known as variable speed of light cosmology, or VSL, was proposed most prominently by physicist João Megiddo as a potential alternative to solve one of cosmology's most vexing problems, the horizon problem. When we look at the cosmic microwave background, the universe's first light, we see a sky that is almost perfectly uniform in temperature. The problem is, regions on opposite sides of the sky were never in contact with each other. Not enough time had elapsed since the Big Bang for light or heat or any influence to travel between them and establish this thermal equilibrium. It's like walking into a vast room and finding that cups of coffee on opposite sides are all exactly the same temperature, even though there was no way for them to have shared heat. The leading solution to this is cosmic inflation, a theory proposing that the universe underwent a period of exponential expansion in its first fraction of a second, blowing up tiny, connected regions to become the entire observable universe. But inflation, while successful, remains a theoretical construct with no direct evidence and some unresolved issues of its own. Variable speed of light cosmology offers a breathtakingly simple alternative. If the speed of light was vastly higher in the very early universe, then light could have indeed traveled across those vast distances, allowing everything to communicate and smooth out into a uniform temperature. After this period of ultra-fast communication, the speed of light would have then dropped dramatically to its current value, locking in that uniformity and setting the stage for the universe we see today. In this scenario, the horizon problem isn't solved by a rapid stretching of space, but by a temporary super boost in the speed limit of causality itself. This idea doesn't stop there. Proponents suggest it could also offer novel explanations for other puzzles, like why the universe appears so remarkably flat and why we see the specific structures we do. Of course, such a radical proposition faces immense hurdles and fierce criticism. Einstein's special relativity is one of the most thoroughly tested theories in all of science. Its prediction that the speed of light is constant for all observers is the bedrock of everything from particle accelerators to GPS satellites. A varying speed of light would seem to unravel this entire framework, potentially leading to violations of causality, where effects could precede their causes, and shattering our understanding of spacetime. Furthermore, any variation in C would have left an imprint on other physical constants and processes, particularly the fine structure constant which governs the strength of electromagnetic interactions. While some highly controversial observations have hinted at a varying fine structure constant, these remain far from confirmed and are hotly debated within the scientific community. The true value of variable speed of light theories may not be in their ultimate correctness, but in their power to provoke. They force physicists to question their deepest assumptions and to explore the boundaries of what is possible. They remind us that our laws of physics, as successful as they are ultimately models based on observations within a certain regime. The extreme conditions of the universe's birth may have operated under a different, more fundamental set of rules that we have yet to fully comprehend. By daring to challenge a constant, these theories open a door to a more dynamic and perhaps even more strange conception of cosmic history, where the very rules of the game were written as the universe evolved. This profound reimagining of a fundamental constant finds a curious parallel in the stellar realm, where certain stars also appear to be playing by a different set of rules entirely. We just explored the radical idea that the speed of light itself might not be a fixed constant, a concept that challenges the very core of Einstein's relativity. But sometimes the cosmos presents its mysteries not in abstract constants, but in the brilliant, visible defiance of its most familiar objects, the stars themselves. In the densely packed cities of stars known as globular clusters, astronomers have discovered a population of stellar rebels that seem to laugh in the face of conventional aging. These are the blue stragglers, and their very existence is a delightful puzzle written in light and time. Globular clusters are among the oldest structures in the universe, vast spherical swarms containing hundreds of thousands of stars, all born from the same primordial cloud of gas at roughly the same time, over 10 billion years ago. Because they are all the same age, their stars serve as a perfect laboratory for stellar evolution. The most massive stars, the brilliant blue giants, live fast and die young, exploding as supernova long ago. What remains are the longer-lived, lower-mass stars that have gradually exhausted their hydrogen fuel and evolved off the main sequence, cooling and expanding into red giants. This is why old clusters are dominated by red and yellow stars. So, finding a hot, blue, massive-looking star in such an ancient environment is as startling and out of place as finding a vibrant, youthful teenager in a retirement home. It simply shouldn't be there. These stars are stragglers, lagging behind their siblings in the aging process, and their brilliant blue color marks them as massive stars that have somehow cheated death. How does a star postpone its retirement? Astrophysicists have developed two compelling scripts for this cosmic rejuvenation. The first is a dramatic stellar merger. In the crowded downtown core of a globular cluster, stars can pass perilously close to one another. Sometimes two lower mass stars, perhaps a binary pair that already orbit each other, can be forced into a collision by a gravitational nudge from a neighbor. When they merge, they combine their hydrogen fuel into a single, new, more massive star. This newborn star has a fresh supply of fuel and a larger furnace, making it hotter, bluer, and brighter than its similarly aged neighbors. It effectively resets its evolutionary clock, appearing billions of years younger than it truly is. The SECOND Chinese letter involves a less violent but equally fascinating process called mass transfer. Many stars in the universe are born in binary systems. If one of those stars evolves faster and expands into a red giant, its outer layers can become gravitationally attracted to its companion star. The smaller star can act like a vampire, siphoning off this hydrogen-rich material from its bloated neighbor. This stolen fuel falls onto the vampire star, increasing its mass and reigniting its fusion processes with new vigor. The recipient star becomes hotter, bluer, and more luminous, a blue straggler, while the donor star is left stripped and diminished. This cosmic theft allows the straggler to extend its life dramatically by topping up its fuel tank long after it should have run out. The study of blue stragglers has given us profound insights into the complex social lives of stars within clusters. Their locations are a telling clue. They are often found right in the dense centers of clusters, where gravitational interactions are most frequent, supporting the collision theory. In other cases, they are found in wider binaries, hinting at the mass transfer mechanism. By cataloging these stars, astronomers can literally map the dynamic history of a cluster, understanding how often stars interact and collide over billions of years. They are not merely astronomical curiosities, they are vital diagnostic tools that reveal the invisible dance of gravity and the secret partnerships between stars. Their persistent youth challenges the simple picture of stellar evolution, showing us that a star's destiny is not written solely at its birth, but can be radically altered by the company it keeps and the encounters it experiences in the bustling stellar metropolis. This intricate dance of stars and their stolen fuel reveals a universe that is dynamic and interactive, a theme that prepares us to examine the very stage upon which this drama unfolds. But if blue stragglers show us how stellar lives can be dramatically rewritten by encounters and theft, our next anomaly reveals that the very fabric of the cosmos itself might have been shaped by a similar, though infinitely more grand, act of rewriting. This is the flatness problem, and it asks a deceptively simple question about the geometry of everything. Why is the universe so incredibly, impossibly flat? To understand just how strange this is, we need to think about the universe's density. According to Einstein's theory of general relativity, the curvature of the entire cosmos is determined by the tug-of-war between the expansion from the Big Bang and the pull of all the matter and energy within it. Scientists define a critical density, a precise golden value that marks the boundary between two fates. If the actual density of the universe were greater than this critical value, the gravitational pull would eventually win, halting the expansion and causing the entire universe to collapse back in on itself in a big crunch. This would create a universe with positive curvature, a closed geometry analogous to the surface of a sphere. If the density were lower, gravity would be too weak to ever stop the expansion, leading to a universe with negative curvature, an open, saddle-shaped geometry that would expand forever into a cold, thin void. Our most precise measurements from satellites like Planck that study the cosmic microwave background have found that the actual density of the universe is almost exactly equal to this critical density. The universe appears to be perfectly flat, or so very close to flat that we cannot measure any deviation. This is the anomaly. For the universe to be this flat 14 billion years after the Big Bang, its density in the first fraction of a second must have been fine-tuned to an astonishing, unbelievable precision. Imagine trying to balance a pencil on its sharpened tip on the day the universe was born, and returning billions of years later to find it still perfectly upright, not having fallen even a hair's breadth to one side. The required fine-tuning is that extreme. The initial density had to be precisely 1 to within 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. Without this impossible-sounding precision, any tiny deviation would have been magnified by billions of years of expansion. A universe only slightly denser would have collapsed long ago. A universe slightly less dense would have become a vast, empty void by now. The fact that we exist in a stable, long-lived universe seems to depend on this initial condition being set with a precision that defies all chance. This profound fine-tuning problem demanded a physical mechanism, not just cosmic luck. The brilliant solution proposed by physicist Alan Guth in the 1980s is the theory of cosmic inflation. This theory posits that a fraction of a second after the Big Bang, the universe was seized by a peculiar form of energy that caused it to expand at an exponential, faster-than-light rate. For a fleeting moment, the universe doubled in size over and over again, inflating by a factor of at least 10 to the 78 in volume. This incredible stretching acted like a cosmic iron, smoothing out any primordial wrinkles or curvature. Think of the surface of a balloon. When it's small, you can easily see its curvature, but if you inflate that balloon to the size of the Earth, its surface would appear utterly flat to anyone standing on it. Inflation did exactly this to the entire observable universe. It stretched space so dramatically that any initial curvature was flattened beyond our ability to detect, naturally explaining why we measure a density so perfectly balanced on the knife's edge today. The power of inflation isn't just that it solves the flatness problem. It also provides elegant answers to other cosmic puzzles we've encountered. It explains the horizon problem, how regions of the universe on opposite sides of the sky have the same temperature despite never having been in contact. Before inflation, the entire observable universe was a tiny, connected speck that easily reached a uniform temperature. Inflation then blew this tiny region up to become everything we can see. Furthermore, the quantum fluctuations that were present in that tiny pre-inflated space were also stretched to cosmic sizes, providing the gravitational seeds that would eventually grow, under the influence of dark matter, into all the galaxies and clusters we see today. In this way, inflation is the foundational event that set the stage for the entire cosmic story, creating a flat, smooth, and structured universe ready for the formation of stars, planets, and life. While inflation is the leading theory, it is not without its own mysteries. The exact nature of the inflaton field that drove this hyper-expansion is unknown, and the theory allows for a dizzying multitude of possible models and outcomes, some of which predict a multiverse of wildly different universes. Nonetheless, the flatness problem remains one of the most compelling arguments for a dynamic and dramatic event in the universe's first moments, an event that ironed out the geometry of reality itself. This grand question of cosmic structure finds a fascinating parallel in the world of the very small, where another precise measurement is hinting that our understanding of the laws that govern particles might also need a fundamental rewrite. From the grand, almost philosophical question of the universe's flat geometry, we now plunge into the subatomic world, where a breathtakingly precise experiment is measuring a wobble so tiny it could herald the next great revolution in physics. This is the story of the Muon G-2 Anomaly, a tale where the 21st decimal place of a measurement might be the most important number in the universe. Muons are often called the fat, heavy cousins of the electron. They are fundamental particles that are identical in every way to electrons, except they are about 200 times more massive and are profoundly unstable, decaying into other particles in just a few millionths of a second. Just like electrons, muons have a tiny magnetic field, acting like a miniature bar magnet with a north and south pole. The strength of this internal magnet is represented by a value physicists call the G-factor. According to Paul Dirac's original theory, this G-factor should be exactly 2, but the quantum world is never so simple. The vacuum of space is not empty. It is a seething soup of virtual particles that constantly pop in and out of existence. As a muon moves through this quantum foam, these fleeting particles interact with its magnetic moment, subtly affecting its wobble, much like a top spinning on a table is nudged by passing air currents. The Standard Model of particle physics, our most successful theory of the subatomic world, has spent decades calculating the precise influence of every known particle and force on this wobble. It is one of the most spectacularly accurate predictions in all of science, calculated to an almost unbelievable precision of parts per billion. This predicted wobble is the universe's official forecast. The anomaly emerged when experimenters decided to put this forecast to the ultimate test. The most famous of these experiments was conducted at Brookhaven National Laboratory and has now been continued with even greater precision at Fermilab. The method is a masterpiece of scientific ingenuity. Scientists create a beam of muons and send them racing around a gigantic, donut-shaped magnetic storage ring at nearly the speed of light. As they circulate, the muons' internal magnets wobble or precess. By meticulously tracking the precession rate of thousands upon thousands of muons, the researchers can measure the experimental value of the G-factor. After years of painstaking data collection and analysis, the results are in, and they are clear. The muons are wobbling just a little bit faster than the Standard Model says they should. The difference is minuscule, but it is definitive and persistent. It is as if the most precise Swiss watch in the world, built to the most exacting blueprints, is consistently gaining a fraction of a second each year. Something is nudging the muon, and that something is not in the blueprints. This tiny discrepancy is a seismic event in particle physics because it is a direct signal of something new. The calculations of the Standard Model are so complete that they have already accounted for the influence of every known particle. Therefore, this extra wobble must be caused by particles or forces that are currently unknown to science. The muons are effectively sensitive quantum sensors, and their unexpected dance is a glimpse into the hidden layers of reality. The most thrilling possibilities include particles predicted by theories of supersymmetry, which posits that every known particle has a heavier superpartner. These shadow particles could be flitting in and out of the quantum vacuum, giving the muon an extra nudge. Another compelling candidate is the dark photon, a hypothetical force carrier that could act as a bridge between the visible world of ordinary matter and the invisible realm of dark matter. The implications of confirming this anomaly cannot be overstated. For decades, the Standard Model has stood triumphant, but it is also known to be incomplete. It cannot explain gravity, dark matter, dark energy, or the matter-antimatter asymmetry of the universe. It is a magnificent palace built on a fractured foundation. The Muon G-2 result is a crack in one of the palace walls, a tangible hint of the physics that must lie beyond. It is a beacon guiding physicists toward a deeper, more complete theory of nature. This is not just an academic exercise. The discovery of new particles or forces would fundamentally reshape our understanding of the cosmos, from the smallest scales to the largest. It is a powerful reminder that sometimes the biggest secrets are hidden not in the distant cosmos, but in the intricate, precise measurement of a particle's delicate dance in a laboratory ring. Yet, even as we chart the ghostly influence of these cosmic deserts, we find that their significance extends far beyond their own empty borders, offering a potential key to unlocking some of the most stubborn puzzles in modern cosmology. One of the most profound connections lies with the Hubble tension, that nagging discrepancy in the universe's expansion rate. Because voids are underdense regions with weaker gravity, they expand faster than the universe as a whole. Galaxies on the edge of a void are effectively being pushed apart by this relative runaway expansion. By meticulously measuring the velocities of galaxies around these emptinesses, astronomers can obtain an independent measure of the local expansion rate. Intriguingly, some studies using this method have found values that lean closer to the higher, local measurements from supernova, rather than the lower value predicted from the early universe. This suggests that voids might be acting as local amplifiers of expansion, and that our position in the cosmos, whether we are inside a relatively dense filament or on the edge of a great void, could subtly influence the measurements we make. They provide a unique, dynamic laboratory for testing gravity itself. Modified gravity theories, like Muon or its relativistic extensions, often make different predictions about how matter should behave in these extremely low-density environments compared to Einstein's general relativity. By studying the subtle motions of the few galaxies that do reside within voids and the delicate lensing effects of their faint mass, scientists are putting our fundamental theories to the test in a regime where the gravitational force is at its absolute weakest. The behavior of nothingness, it turns out, might be the ultimate proving ground for the laws that govern everything. But if the cosmic voids show us how emptiness can actively shape the cosmos, our next anomaly brings us to a mystery that is perhaps the most intimate and universal of all, one that each of us experiences with every passing second, the relentless one-way flow of time itself. Why does time have a direction? Why do we remember the past but not the future? Why does a shattered cup never spontaneously reassemble itself on the floor? This intuitive feeling that time moves forward is so fundamental to our existence that we rarely pause to question it. Yet, when we look at the fundamental laws of physics, from Newton's mechanics to Einstein's relativity to the Schrödinger equation of quantum mechanics, we find something astonishingly bizarre. These laws are almost entirely time-symmetric. They work perfectly well if you run the clock backwards. A video of two planets orbiting each other or two electrons colliding would look physically plausible whether played forward or in reverse. The equations themselves make no distinction between past and future. This presents a profound cosmic contradiction. Our most fundamental theories suggest time should be reversible, but our lived reality, and indeed the entire universe, screams that it is not. The key to unraveling this puzzle lies not in the laws of motion, but in the branch of physics concerned with disorder and energy, thermodynamics. Its second law provides the only known physical basis for time's arrow. It states that the total entropy or disorder of an isolated system always increases over time or at best remains constant. It never decreases. This is why heat flows from hot objects to cold ones, never the reverse. It's why milk mixes into coffee but never unmixes. It's why we age. The universe is on a one-way trip from order to disorder. This relentless rise in entropy gives us a powerful and consistent arrow of time. We can define the past as the state of lower entropy and the future as the state of higher entropy. But this brilliant explanation simply pushes the mystery back one step further. Why was the entropy of the universe so incredibly low in the past? To understand the true origin of time's arrow, we must journey back to the very beginning of everything. The ultimate low entropy state was the Big Bang itself. The early universe was a searingly hot but remarkably smooth and ordered soup of particles, a state of exceptionally low entropy. This is the foundational mystery. Why did the universe start in such a special, finely tuned condition? A high entropy, disordered initial state would have been statistically infinitely more likely. If the cosmos were simply a random fluctuation, we would expect it to emerge in a state of maximum chaos. The fact that it didn't is the reason we have stars, planets, and physicists to ponder the question. This is often called the past hypothesis, and it remains one of the deepest unsolved problems in physics. The low-entropy Big Bang is the ultimate free lunch that the universe inexplicably received, the wound-up spring that has been unwinding ever since, powering the arrow of time and making all of cosmic history possible. Some physicists, like Sean Carroll, suggest that the answer may lie in the multiverse. In this view, our universe is just one patch of a much larger and eternally inflating multiverse. Within this grander structure, while the overall entropy is maximized and time has no defined direction, individual baby universes can spontaneously bubble into existence. By pure random chance, some of these universes will, against all odds, be born in a low entropy state. We simply happen to live in one of those rare, ordered universes where time has a clear direction and complexity can arise. It's a statistical fluke on a cosmic scale. Others look to quantum gravity for an answer. The theory of quantum gravity, which seeks to unify general relativity with quantum mechanics, might ultimately describe the Big Bang not as a singular beginning, but as a transition from a previous state, perhaps a bouncing universe or a quantum fluctuation. This could provide a physical mechanism for why our universe began in such a specific, low-entropy configuration, making the arrow of time not a bizarre initial condition, but an emergent property from a more fundamental timeless reality. The implications of time's arrow stretch far beyond cosmology and into the very nature of consciousness and free will. Our perception of time, our ability to form memories, and our sense of a progressing narrative in our lives are all likely deeply intertwined with the thermodynamic processes in our brains. Neurons fire, chemicals diffuse, and electrical signals travel, all irreversible processes that increase entropy locally. Our conscious experience of the flow of time may be a direct manifestation of the second law of thermodynamics playing out inside our heads. This intimate connection means that solving the mystery of time's arrow is not just about understanding the cosmos, it is about understanding ourselves and our place within it. It forces us to confront whether our experience of past, present, and future is a fundamental feature of reality or merely a compelling illusion generated by the specific, ordered conditions from which we emerged. This profound mystery, bridging the cosmic and the conscious, now leads us to the final frontier of physics, where the quest to understand time itself merges with the greatest challenge of all, uniting the worlds of the very large and the very small. We have journeyed from the enigmatic flow of time to the very edge of our understanding of reality itself, arriving now at what is arguably the single greatest and most profound challenge in all of modern physics, the quest for a theory of quantum gravity. For over a century, we have operated with two separate and spectacularly successful rulebooks for the universe. On one hand, we have general relativity, Einstein's magnificent description of gravity as the curvature of space and time itself. This theory masterfully explains the cosmos on its largest scales, the orbit of planets, the bending of light around galaxies, and the evolution of the entire universe from the Big Bang onward. On the other hand, we have quantum mechanics, the bizarre and counterintuitive set of laws governing the world of the very small. It predicts the behavior of atoms and subatomic particles with unbelievable precision, forming the basis for technologies like lasers, transistors, and the very computer chips that make modern life possible. The problem is, these two rulebooks are written in completely different languages and are fundamentally, catastrophically incompatible. This schism becomes glaringly obvious in extreme environments where both immense gravity and tiny quantum scales must be considered simultaneously, the center of a black hole or the very first moment of the Big Bang. In these realms, our equations break down into nonsense, spitting out infinities known as singularities, where density becomes infinite and the laws of physics simply cease to apply. This is the universe's way of telling us that our understanding is incomplete. We are missing the grand unified theory, the master rulebook that seamlessly blends the warped geometry of gravity with the fuzzy probabilities of the quantum world. Unifying these two pillars is the holy grail of physics, and the journey to find it has given rise to some of the most ambitious and mind-bending ideas in human history. The most famous candidate is string theory. This approach proposes that the fundamental building blocks of the universe are not point-like particles but incredibly tiny, vibrating loops of energy strings. Just as a single violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings vibrate in distinct patterns to manifest as different particles. An electron is a string vibrating one way, a quark is that same string vibrating another way, a photon, the particle of light, is yet another vibration. In this elegant vision, all forces and all matter are unified under the same principle. Crucially, one of these vibrational patterns naturally corresponds to the graviton, the hypothetical quantum particle that would carry the gravitational force, finally bringing gravity into the quantum fold. However, string theory comes with staggering implications, including the requirement of 10 or more spatial dimensions, most of which are curled up into a space too small for us to perceive. A very different path is taken by loop quantum gravity. If string theory tries to unify all forces, loop quantum gravity focuses specifically on quantizing space and time themselves. It proposes that space is not a smooth, continuous backdrop but is instead woven from a fabric of tiny, discrete, finite loops, a network of interconnected threads of gravity. Think of it as the universe's underlying pixelation. Just as a digital photograph is made of individual pixels, space itself is composed of these fundamental grains. This approach brilliantly avoids the singularities of black holes and the Big Bang by suggesting there is a smallest possible unit of space, a quantum of volume, meaning nothing can be compressed into an infinitely small point. The Big Bang, in this view, might not have been a true singularity but a big bounce, a transformation from a previous universe that collapsed. Despite the profound beauty of these theories, they share a monumental challenge, a complete lack of experimental evidence. The energy scales required to probe these quantum aspects of gravity are trillions of times higher than what our most powerful particle colliders can achieve. We are like architects trying to understand the properties of individual atoms by only studying a full-sized building from a mile away. So, how do we test the untestable? Scientists are getting creative. Some are looking for subtle imprints that these theories might have left on the cosmic microwave background, the afterglow of the Big Bang. Others are using precision instruments to see if space-time itself exhibits a tiny, grainy texture at the smallest scales. There is even hope that observations of black holes, the ultimate laboratories for quantum gravity, might someday provide a clue, perhaps through the detailed properties of the Hawking radiation they are predicted to emit. The implications of solving this puzzle are almost beyond comprehension. A successful theory of quantum gravity would not just complete our textbook, it would rewrite it from the first page. It could reveal what truly happened at the moment of the Big Bang, telling us if there was a before and what sparked our cosmos into existence. It could unveil the fate of information that falls into a black hole, resolving the paradox that has troubled physicists for decades. It might even open the door to technologies that sound like pure science fiction mastery over the fabric of space-time itself. While such ideas remain distant dreams, the very pursuit of this ultimate unification forces us to ask deeper questions about the nature of reality, pushing the human spirit to its intellectual limits in our eternal quest to understand the cosmos we call home. And now we arrive at a mystery written in a faint, all-pervasive glow, a cosmic hum of light that has been bathing the universe since its earliest epochs. This is the anomaly of the cosmic infrared background excess. Imagine pointing the most powerful infrared telescope at a seemingly dark, empty patch of sky between the brilliant points of stars and galaxies. You would expect to see nothing, just the black void of space, but that's not what astronomers found. Instead, they detected a persistent, diffuse glow of infrared light, a background whisper that is brighter than the combined light of all known galaxies. It's as if you were standing in a dark forest at night, and after all the visible lanterns were accounted for, you still found yourself bathed in an unexplained, ambient light coming from everywhere at once. This pervasive glow is a real phenomenon, and its source remains one of the most tantalizing puzzles in modern cosmology. This excess wasn't discovered by a single telescope, but pieced together through the painstaking work of space observatories like NASA's Spitzer Space Telescope and the European Space Agency's Herschel Observatory. These instruments are designed to see the universe in infrared light, which is essentially heat radiation. By staring deeply into these so-called dark fields for days on end, they built up an incredibly sensitive picture of the sky. When they added up all the light from every galaxy, they could resolve every spiral, every elliptical, every faint dwarf. There was still a significant amount of infrared light left over. This leftover glow is the cosmic infrared background SIB excess. It's a collective signal, the sum total of countless photons that have traveled across space and time, and it represents a huge portion of the universe's total light output that we cannot directly attribute to any known source. So where is all this extra light coming from? Scientists have several compelling and some exotic theories. One of the leading ideas is that we are seeing the accumulated light from the very first generations of stars, known as population 3 stars. These primordial giants are thought to have been hundreds of times more massive than our Sun, burning ferociously hot and bright before ending their lives in spectacular supernova. They would have flooded the early universe with intense ultraviolet and optical light. Over billions of years, the expansion of the universe would have stretched this ancient light into the infrared part of the spectrum, creating a faint, ubiquitous background glow. The problem is, we have never directly observed one of these first stars. They remain entirely hypothetical. This infrared background could be their collective ghost, the only fossil evidence of their existence. Another fascinating possibility involves dark matter. Certain theoretical models suggest that dark matter particles could be unstable. If they are, they might very slowly decay over eons, producing other particles, including photons of light. If even a tiny fraction of the dark matter in the universe were decaying and emitting light in the infrared range, it could contribute to this pervasive background glow. This would be an incredible discovery, a non-gravitational signal from the dark sector itself, offering our first direct clue to the nature of this mysterious substance that makes up most of the matter in the cosmos. A more conventional, yet still profound, explanation is that our census of galaxies is simply incomplete. There could be an entire population of extremely faint, dusty galaxies that are too dim for our current telescopes to resolve individually. In the early universe, galaxies were often shrouded in thick clouds of dust from frantic star formation. The visible light from their new stars would be absorbed by this dust, which would then re-radiate the energy as infrared heat. Our telescopes might be seeing the combined infrared glow from this hidden population without being able to pick out any single one, like hearing the roar of a distant crowd without distinguishing any individual voice. The upcoming James Webb Space Telescope, with its unprecedented infrared sensitivity, is perfectly designed to hunt for these very galaxies, to see if it can resolve this faint background into countless individual points of light. This anomaly is more than just a missing light source. It's a direct challenge to our models of cosmic evolution. The amount of light in the universe tells a story about how many stars have formed and how much energy has been produced over the last 13 billion years. If we've been missing a significant portion of this light, it means we might be underestimating the total star formation rate in the early universe or misunderstanding the environments in which those stars were born. Every photon in this background has a story to tell, a story of creation in the heart of a star, of a journey through an expanding cosmos, or perhaps of the decay of an unknown particle. The cosmic infrared background is a reminder that even in the darkest corners of space, there are no empty places, only stories we haven't yet learned how to read. And now we arrive at an anomaly born not in the depths of space, but in a laboratory, one that captivated the world not with its profound implications for cosmology, but with its audacious promise of rewriting the rules of spaceflight itself. This is the story of the EmDrive, a concept so alluring and so seemingly impossible that it became a global sensation, a roller coaster of hope, hype, and ultimately, a powerful lesson in the scientific method. Imagine a rocket engine that requires no fuel, no fiery exhaust, no tanks of liquid propellant, nothing to push against. According to Sir Isaac Newton's third law of motion, the foundation of all propulsion, this is simply impossible. For every action, there must be an equal and opposite reaction. A conventional rocket works by throwing mass backwards out of its engine at high speed, which in turn pushes the rocket forward. The EmDrive, short for electromagnetic drive, proposed something that seemed to break this fundamental law. It was a sealed, conical-shaped cavity that you would pump full of microwaves. As these microwaves bounced around inside the chamber, they were supposed to somehow produce a tiny, persistent thrust towards the narrow end of the cone. No mass ejected, no reaction, just thrust from nothing. It was the physics equivalent of a magician pulling themselves up by their own bootstraps. The idea was first put forward by British inventor Roger Scheuer in the early 2000s, and it was met with immediate and deep skepticism from the scientific establishment. It wasn't just a little unorthodox, it appeared to blatantly violate the conservation of momentum, one of the most sacred principles in all of physics. This law states that the total momentum in a closed system must remain constant. The EmDrive, as a closed system with no expelled reaction mass, seemed to promise that you could just turn it on and accelerate forever, creating momentum from nothing. If it worked, it would revolutionize everything. Spacecraft could travel to Mars in weeks without carrying colossal amounts of fuel. Satellites could maintain their orbits indefinitely. It would be the key to the solar system. The sheer potential was so intoxicating that it couldn't be ignored, and so, against all odds, several teams around the world decided to try and build one. A group at NASA Eagleworks Laboratory, led by Harold White, constructed their own version and reported a small but measurable thrust. A team in China claimed similar success. The news exploded across the internet. Headlines proclaimed the death of Newtonian physics and the dawn of a new space age. For a moment, it seemed like a miracle was within grasp. But the scientific process is not swayed by excitement. It is built on a foundation of ruthless skepticism and repeatable proof. As other labs attempted to replicate the results, the story began to unravel. The measured thrust signals were vanishingly small, often on the same order of magnitude as the experimental noise, the tiny vibrations, thermal expansions, and magnetic influences that can easily fool an instrument. The thrust would sometimes change direction if the device was rotated, which made no sense for a genuine propulsion system. The most likely culprit, as many skeptical physicists had argued from the start, was experimental error. One particularly thorough investigation by the Dresden University of Technology in Germany used a sophisticated torsion balance and a redesigned EmDrive. They too measured a thrust, but they also found that the thrust persisted even when they ran the experiment in a way that should have produced zero effect, like using a device that didn't have the internal components necessary for the proposed physics. Their conclusion was damning. The measured force was not coming from some new quantum phenomenon, but from a subtle interaction between the power cables feeding the device and Earth's magnetic field. The final, definitive blow came from a team at the University of Dresden, which built an incredibly sensitive instrument in a vacuum chamber, eliminating the effects of air currents and thermal convection. When they turned on their EmDrive, they detected no anomalous thrust whatsoever. The signal that had sparked 1,000 dreams was almost certainly an artifact, a phantom force born from the immense difficulty of measuring something so tiny while ignoring the myriad of other forces at play. The scientific community, after a long and thorough investigation, largely closed the book on the EmDrive. It was a compelling story, but not a true anomaly. It serves as a powerful cautionary tale about the allure of breakthrough physics and the absolute necessity of rigorous, painstaking testing. It reminds us that extraordinary claims require not just extraordinary evidence, but evidence that can survive every conceivable attempt to disprove it. The story of the EmDrive is not one of failure, but of science working as it should, a self-correcting process that is ultimately more committed to the truth than to any thrilling headline. It is a testament to our boundless curiosity, our desire to test the impossible, and our wisdom to eventually accept the answer, even when it isn't the one we hoped for. This disciplined pursuit of truth, through both confirmed discoveries and debunked myths, is what ultimately builds our real understanding of the cosmos. And so we reach the end of our journey through the cosmos, a voyage that has taken us from the immense, invisible scaffolding of dark matter holding galaxies together to the fleeting, ghostly dance of neutrinos changing their identities in mid-flight. We've stood at the edge of black holes where information itself seems to vanish, peered into the cold spot on the remnant glow of the Big Bang, and grappled with the unsettling possibility that the very constants of nature might not be constant at all. These 25 cosmic anomalies are not merely a list of things we don't understand. They are the very frontier of human knowledge. Each one is a glaring signpost pointing beyond the edge of our current maps, a brilliant and humbling reminder that the universe is far stranger, more complex, and more wonderful than we have yet dared to imagine. This is not a story of failure, but one of incredible potential. Every mystery we've explored is a locked door, and behind it lies not just an answer, but a whole new room of questions waiting to be opened. The tension in the Hubble constant, the missing lithium, the unexplained wobble of a muon, these are not cracks in the foundation of science. They are the chisels and pry bars that will help us break through to a deeper level of understanding. They represent the thrilling, ongoing process of discovery, a process driven by human curiosity, ingenuity, and the relentless desire to know our place in this vast cosmic ocean. For every anomaly that confounds us, there are thousands of scientists around the world designing new experiments, building more powerful telescopes, and performing calculations that stretch the limits of mathematics, all for the chance to glimpse a piece of the truth. As you go about your life, we invite you to carry a little piece of this wonder with you. The next time you find yourself under a clear night sky, look up. Those points of light are not just distant suns, they are the setting for these grand cosmic dramas. They are the homes of potential dark matter particles, the sources of ultra-high energy cosmic rays, and the anchors for magnetic fields that span the void. That sky is the ultimate laboratory, and its mysteries belong to all of us. Your sense of awe is the very same emotion that fuels the world's greatest physicists. Never let that sense of wonder fade. Question what you know, stay curious about the world around you, and never stop marveling at the fact that we are here, right now, able to ponder the deepest secrets of existence. The search is far from over. In fact, it's just getting started. New mysteries are emerging even as old ones are solved. The James Webb Space Telescope is already revealing galaxies that challenge our models of the early universe. The Vera Rubin Observatory will soon begin a decade-long survey that will undoubtedly uncover new celestial phenomena we can't even predict. Particle colliders are probing ever higher energies, and laboratories are growing more sensitive in their hunt for dark matter. The story of the cosmos is still being written, and you have a front-row seat to the most exciting chapters. Thank you for joining us on this incredible expedition. We encourage you to share which of these anomalies captured your imagination the most in the comments below. Let's keep the conversation going. For more journeys to the edge of understanding, make sure to subscribe and hit the notification bell. Until next time, keep looking